Alright, welcome back everybody. I guess this is the grand finale, and the announcement will come afterwards, so thank you. So today I'm going to explain to you the proof of this result that I showed you last time. And so there's going to be two ingredients that I've introduced to you. The first is this result of Schrödinger and Walt that I mentioned last time, which is the group-orders and invariants of statements of positive scalar curvature metrics. So we're going to use that in an interesting way. We'll use it two ways, actually. And the other ingredient is this theorem that I talked about in the first two lectures, which is this result of mine, which are Glacius on classifying spaces of diffeomorphisms, or these modular spaces of manifolds. And I'll come back to exactly why, but for a technical point, I'm going to stick to dimension 6. I've proved the theorem in dimension 6, and because I seem to have written fewer pages today than I did before, hopefully at that time, at the end, I'll explain to you what has to be done differently in dimensions above 6. So let WG, 1 be a 6-manifold boundary. And the following thing, I take a connect sum G copies of S3 cross S3, and then I remove from that an open disk. And I make a choice of such a manifold, okay? So this is just a 6-dimensional version of an orientable surface in genus G with one boundary. And the boundary of this is identified with 5 zero, so we cut out an actual 6 disk. And I'll choose again a collar, which I will is important, but I will probably forget to refer to it. Okay, and then I can consider the space R plus of WG1, so positive scalar curvature metrics on this manifold, and this manifold has boundary, and I've said that I'm probably going to want to have a boundary condition around, and because the boundary is S5, I can ask that on the boundary it's the round metric of radius 1 on S5. So consider that space. So firstly, is this space empty or not? I use Thomas's trick. Anybody know? If the space is empty or not? It's not empty, otherwise why would I be talking about it? Indeed. That's one approach, I suppose. But here's a proof that it's not empty. Okay? We can prove it using this theorem of Schrödinger and Walt from last time. Because we can take this space and we can do surgery along one of the standard S3s inside here. We can in fact do it on G of them. Okay? And because the codimension is 3, and 3 satisfies the inequality from last time, which was that the codimension had to be at least 3, we see that this is homotopically equivalent to R plus of the result of doing that surgery. All the surgery happens in the interior, and so we can talk about having the same boundary condition. Of course, if we do surgery along these G things here, you get a disk. And I asserted last time that there are these things called torpedo metrics, which are metrics on the disk which near the boundary look like a collared version of that. So this contains at least torpedo metrics. So it's not okay. And here's the first, this is probably the main, very surprising input from my theorem. So the group, which I call gamma G1, so this is the mapping class group of these manifolds, it's pi 0 of the group of diffeomorphisms of WG1, and their diffeomorphisms that fix a little neighborhood of the boundary, just like when I was introducing the first lecture. This group acts on this space of metrics. Now, of course, literally speaking, this group does not act on that space of metrics. If I took the diffeomorphism group, then it does. But if I take pi 0 here, then it acts on pi 0 there, I suppose, but it does act on this space in the homotopic category. It acts up to homotopic of this space. The group will act on this in the homotopic category. That's not the theorem. The theorem is that that action factors through an abelian group. Okay? So there are lots of complicated diffeomorphisms here that happen to be commutators of other diffeomorphisms, and those are homotopic to the identity. They induce a map homotopic to the identity of this space. So this is, turns out the proof of this is incredibly formal. And I'll explain the first half of it, and then I'll let you finish it in the exercise session or on the train on the way home. So here's what we do. I'm going to introduce a couple of spaces. First I want to, using the collar, I get diffeomorphisms in the following form. I take WG1, I take the union along the boundary, which is an S5, with, right? And using the fact that this has a collar inside there, I can identify this with WG1 again. I picked some way of doing that that's sort of not stupid. And I also get the same thing when I replace WG1 by the cylinder as well. So I just choose a way of identifying along the cylinder with the standard cylinder. And now, using these, two things happen. One, I can look at the space of metrics on this cylinder, positive scalar curvature metrics, which are the round one at both ends, at either end. And given two such metrics, I can just glue them together to get a metric on this, which is round at either end, and then I can use my diffeomorphism to put it back in the same manifold. So this becomes an H space via gluing and 2. Okay? So that's the first thing. And the second thing is that the metrics on my interesting manifold, WG1, then becomes that H space analog of a module. Right? It has an action of this H space up to horizontal. Is an H module over the first thing. Okay, and there's one more thing we have floating around, which is the topic of this, of the statement, which is that the diffeomorphism group acts here as well. So actually, let me give these some short names, so I don't have to keep writing it. I'll call that Z, call that X, and I'll write G for the diffeomorphism group. Okay? And the first observation, the Z action and G action on X commutes up to homotopic. Or distribute over each other, whatever you want to call it. Okay, so not on the nose, but up to homotopy. So why is that? So we can take some metric on the manifold W, and we can take a diffeomorphism of W. We can change the metric by the diffeomorphism, and then we can glue on some other metric, G or H. So that's doing one thing, that's to do the diffeomorphism first, then you glue on H. Alternatively, you start with the metric you had, you glue on H, then you consider that to be the manifold WG using this diffeomorphism, right? And then you act sort of on the whole thing Okay? But because these diffeomorphisms have to fix the neighbourhood of the boundary, you can just make it fix this whole H string, and then you get what you have to do. You just isotope phi so that it fixes a long column instead of a short column. Okay? And that gives a homoton. And now this puts one in a surprisingly sort of, I don't know, sorry, there's one more, that's one observation. Two more observations. The second one is that this monoid Z, or Z, is commutative up to homoton. And that's not so obvious. I have a metric on a cylinder and another metric, and I think the other way around. There's no especially obvious path between them. And this is where we use this fantastic result of Schoenisch and Walsh. So I can define two sub-H spaces, plus minus, G ground. So these are the subspaces of G, which are those metrics which on 0, 1 cross the upper or lower hemisphere, depending on what my declaration is, are standard. Let me just say. So they're dt squared plus some standard metric that I've chosen there, the lower hemisphere metric. Okay? So I have two sub-H spaces, and clearly composition, if you have two things that are standard on the bottom, you glue them as standard on the bottom. So these are sub-H spaces. And they clearly commute with each other up to homoton. I've got something that's standard on the lower hemisphere, and something that's standard on the upper hemisphere, and I put them next to each other, I can then just slide them past each other. So these are two sub-H spaces that sort of commute with each other up to homoton. So these commute with each other. But in the notation that I was using last time, this is just R plus 0, 1 cross S5, comma, subspace 0, 1 cross D5 plus or minus, with some it's just this notation I introduced, this metric that's standard on a hand. Right? And the theory said that the inclusion of that into all metrics is what's called Z, is an equivalence. So you've got an H space, it has two homotopy equivalent sub-H spaces that commute with each other, so the whole thing is homotopy commutative. Pretty cool, and that's the first application of this result. Now we're going to apply it again to get the third surprising thing, which is that there exists some metric in X. X is the space of metrics on the interesting manifold. Such that sort of acting on that metric, which is the map from Z to X, we take one fixed metric on the interesting manifold and you glue on a cylinder in all possible ways, with all possible metrics, so that that's an equivalence. So this is, if this was a group and that was a set on which it was acting, this is what it would mean to be a torsor. Right? It acts sort of freely and transitively. If you take pi 0, it's in fact saying it's a torsor. Okay? Now, if it was a group acting on a set, then any choice of G naught works. Unfortunately, we don't know that pi naught of Z is a group. It's a monoid, so we know how to compose, but there's no reason to think that you have inverses there. So there you have to state this a bit more carefully, that there's a particular one that works, rather than that any one will work. So what's the proof of this? Well, let me stop writing the boundary condition. The boundary condition is always the round metric component. Okay. So what I want to do, so we have this, we have the map that, no, what is that? We have this square that I used when I was proving the cobordism invariance. Right? Inside here you have the things that are standard. Things that are standard on G copies of S3 plus D3. Inside there, and it's an equivalence by the Schoenisch-Walsh theorem. On the other hand, you can do that surgery, and then you get into the space of metrics on the disk, which are standard in some, I guess some formulas. That's also an equivalence like the Schrödinger theorem. And all this stuff happens, you see, away from the boundary. So all these maps are maps of Z modules, if you like. Okay? I mean, they commute up to homotopy with gluing on the cylinder outside because it isn't really going near the boundary at all. So that shows that this, which is the one called X, X is sort of homotopy equivalent as a Z module with the metric on the disk, standard on the boundary. And that has this property by, again, the Schrödinger theorem. What is that? Another way we can say it, we could also say metrics on the disk, which are standard on a smaller disk. By the Schrödinger theorem, that's a zero handle, right? But what is this? This is just metrics on a cylinder, and I'm acting by metrics on a cylinder, and that's clearly a free module, and in particular it has this property. So this is just homomorphic to Z again. Okay, so yeah, check all these sort of module maps and so on, but that gives this property. And now it's a purely formal argument, very similar to the argument that pi2 is an abelian group. That if you're in this situation, the group G acts via the monoid Z in the homotopy category. Implies that pi naught G acting on X in the homotopy category, which is the only place to make sense, acts via pi naught of Z. And I'll leave this as an exercise because it's quite a charming thing to work out. But what is pi naught Z? Pi naught Z is a monoid, which is abelian because it was homotopy commutative, and then we took pi 0. And the other thing is a group, and you have to think for a second that if a group acts through an abelian monoid, then it acts through an abelian group. That's true. And that's the end of that. So I do recommend that you do this exercise. It's not very difficult. You use precisely 1, 2, and 3 to do it. Okay, so now I can come to this. This is the technical result that we need for the proof. Now I can come to the proof properly. So we choose once and for all embeddings from each of these WG1s into the next one. Such that the complement of each one is a standard thing. So such that each complement is K, namely 0, 1 cross S5, and X sum S3 cross S3. Or is the insist if you want it to. Okay? You should make that choice once and for all. Also choose a metric on this K which is around one of either boundary, and this has to have one property. It just has to be in the y component. Okay, so the space of metric, the active metric doesn't matter, it has to be the y isotopic class, and it has to be in the component corresponding to DC squared plus G round in the space of metrics on the cylinder, corresponding under what? Well, under the homotopy equivalence between that and that, that's given by soldering these away. Under the equivalence. By surgery on free cross D3 in some standard way. Okay. So remember, the result was actually a little bit stronger. The actual proof of the Chernich-Schwarz theorem was stronger than the actual statement. Not only a choice of surgery data gives you a choice of homotopy equivalence. So there's a preferred homotopy equivalence, and here I have my preferred cylinder metric, and I take any one that's in the right component back there. So let me introduce some notation. You write D, this is just to shorten everything. DG is going to be the diffeomorphism group well boundary of this WG1. Okay? So extensive gluing on K gives homomorphisms DG, D, G plus 1, and so on. The second thing, I'm just going to write RG for space of metrics on WG1, sorry. The round one on the boundary, and again, gluing on the metric on K gives a map, I should probably give it a name, call it union GK. It goes from RG to RG plus 1. And this is equivariant for that, obviously. God, does that look the name? No. That gives R, which is DG equivariant. Where DG acts on this side through this one. So now we can use the Chernich-Schwarz theorem again. So use it all the time, it's fantastic. There's only one trick. And what I want to claim is that this is a homotopy equivalence. And that's going to be because I chose my GK in the right way. It's not going to always be true, it's because I've been careful how I choose it. Okay? But the claim is that this map by gluing on GK is a homotopy equivalence. How do we see that? So the point is that it factors through something a bit better, right? We take any metric on WG and we go on a standard metric. So by definition, it factors through the metrics which are standard, okay? Right? And in particular, they're standard on a little handle inside K. So this factors through R plus of WG plus 1, comma, standard on the S3 plus D3 that's inside the K, the last K that we glued on. Okay? And then that's just a space of RG plus 1. Okay? By the Chernich-Schwarz theorem, this last thing is an equivalence, forgetting that it's standard is an equivalence. So we just have to show that the first map is an equivalence. Okay? But on the first map, we can now, in here, we can just do surgery on that handle. And you get a map, or you get an identification with R plus of WG union of cylinder. The standard on the corresponding dual handle, which is a V4 cross S2. And again, you can include that into R plus WG maybe I use my diffeomorphism to put the cylinder back in again, so it's just WG again. Okay? And again, by the clonation order, and that's equivalence. But the whole thing is just the identity map now. Right? You've glued on something complicated and you sorted it away again. So the whole thing is given by gluing on. Oh, so maybe I shouldn't have identified that. Let me just make this the actual include. The whole thing now, by the way that I chose my GK, is given by gluing on the cylinder metric, which I had written there somewhere. Where have I chosen GK? Is it there? Oh yeah, right. It's given by gluing on dt plus g squared. So this is given by gluing on dt squared plus g round, and it's sort of clear by some sort of stretching argument that gluing on the cylinder metric you can just squeeze it in again. Right? So that's almost equivalence. So that proves that. Fine. So now we have this, we have an actual map that's actually equivariant for DG, and it's the homogeneous equivalence. One more piece of notation that I should have written up there, we didn't use it yet, so I can write it here. Let me write xg for the Borel construction of dg acting on rg. So this is e dg cross over dg with rg. Okay? So it's the total space of the five model with base, the classifying space of dg, and with 5 with the space of positive scalar coefficient metrics. And now one can draw the fundamental diagram that goes like this. Rg, xg, classifying space of dg. So that's just the canonical fiber bundle that comes from this being the Borel construction, and that's acting on that. And now, because my map was dg equivariant, I get an induced map of Borel constructions. Map that I chose, and maybe I should give this one a name. This one there's only one homomorphism between dg and dg plus one that will ever show up, and it's always that much. So we can now just keep doing this. And over here, let me write x infinity for the homotopy covert, or the mapping telescope of this sequence. And let me write b d infinity for the similar thing down here. And I get an induced map, and I call this pg plus 1. There's a small technical thing here. Mapping telescope of Serre vibrations isn't a Serre vibration, so I then have to replace this by a Serre vibration, which I just do silently. Okay. In a standard way. And this has some f, which is the homotopy fiber of things. Okay? And what do we know? Well, by the claim that I just made, all of these top maps are homotopy equivalences. Okay? So all of these squares are actually homotopy fallback squares. Okay? And this is somehow the entire, this is my view of the whole positive scalar curvature story. You see, because of this Boltzmann invariance of the space of metrics, you can start with some simple manifold like a sphere, and you can try to act by diff using this Hitchin construction that I said. You pick one metric and you act by a diffeomorphism. And the sphere's got some interesting diffeomorphisms. But by the Boltzmann invariance, you can replace it by adding on all sorts of other mesh that doesn't change its Boltzmann class, but that makes the diffeomorphism group be tremendous. Okay, and you haven't changed up to homotopy the space of positive scalar curvature metrics. And so this is just taking that to the logical conclusion and taking a limit of attaching arbitrarily many S3 equals S3s. Okay, so this F is up to homotopy is the space we're interested in. I guess down here I have are 0 if I went off this way. Just metrics on a disk. Those are references as well. Okay? So now, right.
So far, this is just the orbit maps of all these different.
Yes, yeah.
We're not sure the data.
Right.
Nothing happens.
So how can I use this to get information? Well, I wanted to get a map into this space of positive scalar covariance metrics from something, right? So I can get a map into this one because it's homotopy equivalent. And an obvious thing I can do is I can just loop this vibration up once and get a map from d infinity to here. But that's just the obvious thing. That's just a diffeomorphism acting on metrics by putting them back. We haven't done anything clever there. So what I want to do now is that the theorem I told you about with Galatius, or let me remind you what it says. It says in this dimension there's a map from d infinity. I was doing some colimits of multi-spaces of manifolds, but it's exactly this colimit, to the infinite loop space, or in this case MT spin 6, or a component of that. And let me just remind you here, MT spin 6 is the Thom spectrum of, you take E spin 6, and you take minus the canonical 6-dimensional envelope of that. Okay, so you can't do that as a Thom space, which is a spectrum. You can take Thom spectrum of a virtual body. So that's what that was, and this was the Pontryagin Thom map. And the theorem was, this is a homology of normal. That was the theorem, okay? And that's what I want to use at this stage. This space is this space. Now, I can do what I just said. I can loop this up here, and I get d infinity. And I can take this map and I can loop it, and I get a map from d infinity to something. And if you remember the statement of the theorem, that something is the thing that I'm claiming maps to, I suppose. But if you take a map which is a homology equivalence, and you loop it, it becomes nothing in particular. It's not a homology equivalence. This is massively non-simply connected. Right? Pi 1 is the mapping class group of this infinitely complicated manifold. Looping it is crazy. So we don't want to do that. But we want to very nearly do that. And here's where the only restriction, this is the only reason why I'm doing this in dimension 6, is that the following remarkable fact. H1 of the right-hand side space, loops infinity 0, MT spin 6, with integral coefficients is 0. Is a fact that I'm asserting for you, and let me just relate it to a similar fact. So it's H1 of an infinite loop space. Okay? So it's an infinite loop space, so its pi 1's already abelian. So H1 is the same as pi 1 by H. This is pi 1 of the same thing. And on the other hand, pi 1 of an infinite loop space is the same as pi 1 of the spectrum. So this is the same as pi 1 in the spectrum homotopy MT spin 6. Okay? And if I hadn't used B spin 6, but I'd used B spin, the thing that you're used to, here, because of this degree shift by minus 6, here I would have got 7th spin bonds. If I take pi 1 of basically the 6th d suspension of M spin, that's by definition spin Bordism. And the only difference between that and this is that here I'm using the unstable group B spin 6 as opposed to the stable group B spin. Okay? But you know, because Dermot told you a couple of days ago, that this group is 0. That's the fundamental tool for all his talks, is that if you have a spin 7 manifold, it bounds to spin 8 manifold. Okay? Now, it's a fact that this group is in fact 0. Okay? And one proof is starting from the fact that you know that. Then if you want to show this group is 0, you can just study the difference between these two spectra, and you can compute the fibre of that map of spectra, and you can do like atom spectral sequence or whatever you like doing to compute homotopy groups of spectra. Okay? But here I'm just going to present it as a fact that this group is 0. But what does that mean? That means that I now have a homology equivalence to a space which is simply connected. So let's try to apply Whitehead's theorem in homology. Whitehead's theorem in homology says that if you have a map, wait, no, that's not what I want to say. Let me go back a second. We'll do that in a minute. So the right-hand side is simply connected, and so has trivial first homology, and so, by the theorem, the left-hand side also has trivial first homology. The map is a homology isomorphism. And what is this? This is the abelianization. This is, I take the colimit as g goes to infinity of my mapping class groups g1, and then I take the abelianization. That's what that is. So what this, right, this colimit is the fundamental group of this colimit of spaces, and homology is taking abelianization. So what this fact means is that this group has trivial abelianization, i.e. its commutator subgroup is the whole group. If you let me write gamma infinity for this colimit, the point is that the commutator subgroup of gamma infinity is the whole thing. Okay? And now we put literally 2 and 2 together. We have a fibration. We know that pi1 of the base acts on the fiber through an abelian group, because that was true all the way back here when you easily check that passes to colimits. And on the other hand, we know that the abelianization of this group is 0. So that pi1 of that acts on the fiber through the 0 group, i.e. acts trivially on the fiber. So one consequence is that pi1 of this g to infinity acting on f is trivial. Okay? And so these are, I don't want to deduce that from this, these are 2 facts that I'm going to need, 1 and 2. Okay? Right, how can we use this? Question? Did I hear somebody snuffle? No? The way I want to use this is, groups that are so-called perfect, which is the name of this property, is equal to its commutator subgroup. Play an important role in algebraic K-theory. Quillen's definition, or one of the many definitions of algebraic K-theory, is you take a ring, you take its general linear group, you take a classifying space of that, you nominate a certain perfect subgroup, which is the subgroup generated by the elementary matrices, and you do something with respect to that subgroup. And that something is the plus construction, which I'll just remind you about now if you're not familiar with that. Quillen's plus construction. So the plus construction says I've got X in space, may be connected, and I've got P, a normal subgroup of the fundamental group of X, which is perfect. This is the setup, and the claim is then there exists a map A from X to a new space that's called X plus, such that 2 things hold. 1, P is the kernel of the map induced by A on pi1. So you've exactly killed this group that you started with, and pi1A is onto it. So pi1 of this plus construction is the old pi1 modulo the group that was perfect that you wanted to kill. And of course, it's not difficult to make this happen. You start with X and you attach them 2 cells to kill the genus of this group. That doesn't need to be perfect, notice. But the amazing thing is the second point, and this is where the perfectness comes in, which is that the map A is an isomorphism on homology. Right? If you just take your thing and you attach some 2 cells to change the fundamental group, then you're definitely changing the homology. And what Williams shows is that you can then attach, using the condition that's perfect, you can then attach them to 3 cells, which homologically kill the 2 cells you attached. And that's the result, basically. And that uses the perfectness in the important way.
They're saying that given any perfect subgroup, you can do this?
Yeah.
Okay.
Yeah.
There's different construction rules. Okay. Possible perfect subgroup.
Oh, I mean, you can make it functional if you want to. The naive way is that you have to pick certain generators and you can make them be products of commutators because it's perfect. And then you think about what that does to H true or pi true of the universal cover, and then you attach some free cells to undo that homology. But I mean, any construction that starts with attaching cells to kill homotopy, you can always make functorial by attaching cells along every continuous map that's in the white homotopy class. Make some homotopy gate construction. Let's see, let me keep that. So I want to apply this plus construction to my BD infinity. What do I need? I need to nominate for you a perfect subgroup, and luckily I have a perfect subgroup, which is the whole fundamental group. I apply this to BD infinity, with P being gamma infinity being the whole group. Which is perfect by 1 up there. And I get a map A from BD infinity to BD infinity plus. This is now simply connected because I've killed the whole fundamental group. So this is one connected, and the map is a homology of okay. Now I've just remembered I've misstated, or I haven't quite, but one can upgrade this slightly to saying that A is an isomorphism in any homology or cohomology group. So I can use A. And which cohomology theory do I want to use? I want to use the one represented by the infinite loop space, loops infinity empty spin 6. So what does that say? I have, so now I want to think of my map alpha as being a which it is, a cohomology class in empty spin 6 theory of BD infinity. What does that second property say? It says that I get a bijection between cohomology groups, empty spin 6 cohomology of that, and empty spin 6 cohomology of that, i.e. this map factors through that. Autonomous alpha plus. And now we can do what I almost jumped ahead to last time. I want to apply Whitehead's theorem. I now have two simply connected spaces, and I have a map which is a homology isomorphism, because that is and that is, and so that is. Homology equivalence of this space. So this is the first step, okay? I haven't used 2 yet. I haven't used 2. The way I want to use 2, I just have to state this as a fact. This is a fact. The reference I have for it is due to Barrett, but there may be an early one, because I'm probably using a very special case, which says that if F, E, B is a vibration, and I1 of the base acting on F is trivial, then F, E plus, E plus is a vibration. Okay, so I don't construct that.
So what, I mean, plus means...
Plus means now, oh yeah, okay, so plus, if I don't nominate a perfect subgroup, there's always, just by form of property, a maximal perfect subgroup. Because any two, the thing it generates again perfect. So I always mean with respect to the maximal one if I don't say which. Right. So again, I mean, if you don't know about the plus construction, this might just seem like some black magic, but once you know that the base acts trivial on the fiber, then you can prove this sort of thing with like a set or sequence or something. That's how that gets used. So what does that mean? I can now come back up to my diagram and I can extend it one step to the right. And that we've got F for that.
In Barrett's theorem, is that with respect to functorial plus construction? Or, I mean, if I take any plus
Oh, when I
construction...
say a fibration, I don't literally mean that the actual on-the-nose map is going to have the homotopy property. I mean, it's like a homotopy fiber.
Okay, all right.
Yeah.
Yeah. Thanks.
Right. So what I really mean is that the map, there's a canonical map from F to the homotopy fiber of that in that sense. Here, this F should of course be the actual homotopy fiber of that. And the way I'm using various statements to say it. Good. Because now we can loop this vibration up. And this is now a simply connected space. And looping those is a lot happier than looping things with massive functions. In fact, let me now at this point apply the theorem that's on the board behind here, which says that this is equivalent to 0 and T36. Yeah, right, that result. And now I can loop this up, and I get a map. In the statement of the theorem I was saying below, it goes from loops infinity plus 1. Right? I loop this one more time. And this spin 6 to, well, in principle, this homotopy fiber. But then I can invert all of these weak equivalences and come back down to positive scalar cogeometrics on the disk. Bit of standard note there. Now, the statement of the theorem, here I had any manifold. But the point is, once you prove it for a disk, you can then plug a family of metrics on a disk into any manifold. By picking some way and extending it. So this thing just, for free, proves a more general statement. So I get a map, right. So I want to spend a minute, so the theorem had two parts. One, it says there's a map, and the second part says if I do this and then the index difference map, that's the KO theory Tom class. Okay? Without that, the theorem is not so useful because you don't know anything at all about this map. It's constructed, you would agree, in an indirect way. What one needs to do to prove the P equivalent with respect to this index difference is think about the index difference construction all the way through the argument. And what I want to do, remember I started with this square. There's some manifold with a boundary, with a metric on the boundary. I have this square. Where this was the index map, and this was this theorem due to Lichtenowitz, Weizenbach, Schrödinger, that if you start with a positive scalar cogeometric, then the Jacob wedges invert. Okay, this was the square I started with, And remember, I use this to get a map from this to loops on that by choosing on the topic of these two maps. And this was again loops C, C++, for the purposes of that row to follow. So now, the point is that this can be made diff-W equivariant, this whole setup. And we'll have to be a bit careful about that, because what do I mean? Here I've said, what is this? Clifford D, self-adjoint, graded, bounded operators on a Hilbert space. Well, which Hilbert space? Because here it's acting on the L2 sections of something over W. Right? So implicitly that's the Hilbert space I'm using. So if I try to make this equivariant, I ought to have diff acting on the Hilbert space over here. But luckily, that action will be through the unitary group of the Hilbert space, which is contractible, like Cooper's theorem. So in fact, you can just do the naive thing, you will go wrong, but you have to understand why you will go wrong. So what you can get out of this is, oh, okay, I haven't used it before. I'm going to write double slash for a Boole constructor. So you can upgrade this to an equivariant square like this. And what did I say? I said that's contractible, and this is the space that represents D or minus D real K theory. So what I have here is an element, I think it's called beta, in KOD of this space relative to that space. Kind of relative K theory class. Now this space, the space of all metrics is contractible, so this is just B diff. I'm going to write it that way. Yeah. Okay. And this has two properties, which relate it to, on the one hand, the index, and on the other hand, the index difference. So, I'll get this right. This satisfies one, the underlying absolute K-theory class is just a family index. So that is in K minus D or B diff. And W. And what is this? Well, B diff W has by definition this universal family of manifolds of dimension D over it, and it's the family index of that family. And the second thing is that one can transgress this. You know, this is a fibration basically over here with fiber, the positive scalar curvature metrics, and you can transgress it to get a class on the fiber. So the transgression of this beta is in KO minus D minus 1 of R plus WH is the index difference. So that's somehow the relation between these. Right. Have I? Oh, good, I haven't erased my big diagram. So at each stage here, yeah.
What's the first statement?
The first one, I don't even read that. Underline.
But what about the underlying?
So it's the,
Oh, so it's the family index.
Ah,
Yeah.
so it's just the bottom horizontal map in this square.
Sorry, yes.
And the middle square, and the square shows that it transgresses to the fiber.
Right. Yeah. So what happens? Well, I can do this for each of these vibrations. So I get a beta G here, a beta G plus 1 here, a beta G plus 2 there. And get beta G, KO minus D of VGB into XG. And let me just write it this way. These can be shown to be compatible with varying G. So if I take the one here, you can want to pull it back, I get beta. So this is sort of thing that I certainly can't do. This is Johannes Everett's work. And there's one underlying fact, which is that there are two convenient choices. I gave you one definition of this index difference map. There's another definition you can use, and they land in the same group, and clearly they better be equal. So Johannes has a 30-something page paper about that proves that they are indeed equal. But that's a quite involved fact. Although he once to me called it an exercise, but
I think that's not what I write in the paper. This is actually, this part is they use this theorem by Bunke.
Right.
Which is an exercise, but it was non-trivial. It was Bunke's work plus a fairly big epsilon.
Right. So there's another point. Right. So the other input is a sort of additivity theorem for this secondary index when you cut causals apart and glue them together differently. So these are this is serious index theory work, at least as far as I'm concerned. But the result is that one gets a beta infinity in KO minus D of the infinity x infinity. Not perhaps canonically, because of some lim1 unpleasantness, but you certainly do get a class that restricts to the to beta G. Because the plus construction doesn't change generalized cohomology, as I had somewhere, I also get a class in here, formally. And so there's a class that's in the relative K-theory of that. And if I write that on the space level, what does that mean? I have this vibration on the rightmost vibration, x infinity plus, infinity plus, and I have a relative K-theory class for this map. So what does that mean? It means I've got a map basically, let me write it this way. Like that, which commutes. And so I can take a fiber here, and I get a map to loops for D. And by this property 2, this map will be the index difference, because that's just a translation construction. So this is and I've got a little bit lost. Remember the index difference, I made a big point about that you have to choose a base point. But that shows up here because you have to choose a point over which you're going to loop and over which you're going to take a fiber. So I like that. Right. And on the other hand, this down here, the index, so that's by definition. Or let me say, if you go back here at least, this is the index. And now I want to say that under my identification of that with loops infinity MT spin 6, that this map is the KO theory atomic class. And that is the associating an index theorem, saying that the index can be computed by the push forward in real time. So this is the alpha, is the map. Oh, my D's are D should be 6 everywhere. I'm doing the math mistakes, sorry. So this is the map alpha by Tisser map. Right, and that's the end of the proof. If I have 1 minute, I just wanted to point out, so I said that I went through everything in dimension 6. The only time I used that was for this fact. This fact is not strictly necessary, although it's convenient for, because I can go through the proof quicker. The important point we need, so all we needed was that gamma infinite, that the commutator subgroup is itself perfect. That's all we actually needed, right? Because then you can plus construct that. That has the effect of abelianizing pi 1, and so this now becomes a pi 1 equivalence as well. Yeah, something like that. And I just want to point out that this is, for groups that are constructed in this sort of infinite way, by gluing together many copies of the same thing, this is a completely general phenomenon. It's called quasi-perfect, and it's almost always true for groups constructed in this way. For example, it's a complete formality, even if you didn't know that the alternating group A5 was perfect. Suppose you didn't know that. It's a complete formality that A infinity is perfect. Which is the double commutator subgroup of sigma infinity. I just want to explain that because I think this is a fun point. So, so the setup is that you have a sequence of groups, Gn, and you have sort of product maps, Gn cross Gn to Gn plus m, called mu m, that are commutative up to conjugation. So mu n m is conjugate to mu n n precomposed with the twist map. Okay, so suppose you have that situation, then you can take G infinity to the product of Gn overtaking product with like the unit in G1. Mu1 and 1 down. Take that to your single group, and it's an easy theorem that G infinity prime is perfect. Which I'll leave to you to prove. In fact, you prove a stronger thing. You prove that every commutator is in fact a commutator of commutators. Never one product of commutators and rubbish like that. Because any commutator you can rewrite as a commutator of commutators. So that's another exercise. So this, you do this exercise, and you should do the one about a group with a monoid and a group, sorry, a set with a monoid and a group acting and a commutator. Those are two exercises that are complete trivialities, but fundamental to the proof. One final thing, if I may, being the last speaker, it's my privilege and pleasure to invite you to thank the organisers of this fantastic conference.
I have one. So do all your elements die when you go to the moduli space?
Right.
Reminding metrics, I mean, in the end,
You need to divide out by diff, yes. So, because of this Boltzmann invariance, that's the wrong question. Sorry. So what you want to say is you take R plus of some manifold W, and because of this Hitchin construction, you know that one way to get things is to take one you know and put it back by a diffeomorphism. So let's get rid of that by taking the quotient of the major well construction by and define that to one of that space of PSC metrics as well. So that disallows you doing Hitchin's trick. But because of the Boltzmann invariance, you see, it's somehow, if you've got a manifold W, why just disallow the diffeomorphism group of W? You know you're allowed to change the manifold by Boltzmann when you don't change the space. You do change the diffeomorphism group. So somehow this is, I would say, not a good question. But it's definite. So here's something that's definitely true. You know, I proved it. In the end, we got maps. We got PSC metrics on a disk, and it's definitely true that all the things we compute are non-trivial in the space for S6, for example. So there, all the things you get is still, or at least the rational stuff you get is still not true. But that's somehow because you've changed the man box. It's so simple that all the different motions you have are kind of don't do much interesting rationally.
Final opportunity to say something.
I mean, the point is you can't, if you're in a single manifold, if you're in a single manifold and you want to see a homotopy class in the space R plus modular space, you can't possibly see it with the index difference. There is no index difference on this space. It simply doesn't exist.
Ah, yeah.
I mean, you have no way to detect it.
Right, I mean, that's what I was doing here, you see, by definition, the total space, the thing that it mapped to was the invertible operators, which is contractible. So you get something downstairs and you get something upstairs, but in the middle you don't get anything. So you have to rule this out. You've got to use that you know just enough rational stuff there, and you know that this is rationally, there's not enough there to get it.